Hello. In this section, I will tell what is really inside a lithium-ion battery. In the last 2 decades, the global demand for lithium-ion batteries, LIBs, has increased dramatically, reflecting a profound shift in the way modern societies store and consume energy. These batteries are now found in a wide range of products, from smartphones, laptops, and power tools to electric vehicles, EVs, stationary energy storage systems, and even aerospace applications. According to Bloomberg NEF forecasts, global battery demand may exceed 5,500 GWh annually by 2030. This transformation is not without consequence. It brings a host of challenges related to sustainability, resource scarcity, and end-of-life management. From the perspective of the circular economy, CE, LIBs are more than just hazardous waste. They represent a rich reservoir of secondary raw materials that, if properly recovered, can reduce dependency on primary resources, improve supply chain resilience, and support environmental and economic goals. Metals like lithium, Li, cobalt, Co, nickel, Ni, and copper, Cu, which are essential for LIB functionality, are finite and often sourced from geopolitically unstable regions. This highlights the urgency of developing efficient and sustainable recycling strategies. Moreover, the rapid evolution of battery technologies, such as the transition from LCO to NMC or LFP chemistries, further complicates the recycling landscape, making material tracking and recovery even more essential. Europe, aiming for green energy autonomy, must design strategies for reclaiming materials within its own economic system, ensuring that batteries do not become liabilities but valuable sources of critical resources. This article aims to present an in-depth analysis of the physical and chemical structure of lithium-ion batteries, explore the composition and strategic relevance of key components, and assess the implications for circular economy models and raw material sovereignty in Europe. A lithium-ion battery is composed of individual cells, modules, and packs, with each layer serving a specific function. The fundamental electrochemical unit is the cell, which stores and delivers energy through redox reactions. Cells are typically manufactured in 3 main formats: cylindrical, e.g. 18650 or 21700, prismatic, and pouch. The format impacts the battery's energy density, cooling efficiency, packaging flexibility, and end-of-life disassembly. Each cell includes the following core components: anode, typically composed of synthetic graphite deposited on a copper foil current collector. The anode hosts lithium ions during the battery's discharge phase. Cathode, composed of metal oxides containing lithium, cobalt, nickel, manganese, or iron, coated on an aluminum foil. The cathode is the main source of lithium-ion transport during charging. Separator, a thin polymer film, usually polyethylene or polypropylene, that physically separates the anode and cathode while allowing lithium ions to pass through. Electrolyte, a solution of lithium salts, commonly LiPF6, dissolved in a mixture of organic solvents such as ethylene carbonate and dimethyl carbonate that facilitates ion mobility. Battery modules consist of multiple cells connected electrically and thermally managed within a protective casing. Modules are then assembled into battery packs, which include additional components such as battery management systems, BMS, thermal management units, sensors, wiring harnesses, and protective housings. Beyond these components, modern EV batteries also integrate passive and active cooling systems, fire retardant materials, vibration dampeners, and intelligent monitoring units. These additions contribute to the complexity and cost of battery recycling and must be considered in end-of-life logistics and dismantling operations. Overall, a large traction battery for an electric vehicle may weigh up to 600 kilograms and contain thousands of individual cells. The dense, modular architecture of these batteries makes them both technologically sophisticated and logistically challenging from a recycling perspective. Their structure demands specialized disassembly, fire-safe storage, and precise sorting technologies. Understanding the material composition of a lithium-ion battery is crucial for designing efficient recycling processes and assessing the potential for critical raw material recovery. A typical LIB contains a wide range of valuable and strategic materials distributed across its components. The approximate weight distribution for a standard EV battery is as follows: battery housing and structural parts, 25%, cathode materials, 25%, anode materials, 14%, electrolyte, 10%, copper foil, 8%, aluminum foil, 6%, separator, 5%, electronic components and other materials, 7%. This breakdown underscores the importance of targeting high-yield materials for recovery. While plastic housings and electronic components may offer limited recyclability, the cathode and anode layers are prime candidates for economic and ecological extraction. Cathode materials. Cathodes contain the most economically and strategically significant metals. Depending on the chemistry used, cathodes may include cobalt, so common in LiCo2 and NMC cathodes. Cobalt is expensive and associated with ethical sourcing issues. Nickel, Ni, improves energy density. High Ni chemistries such as NMC8111 are increasingly favored. Lithium, Li, present in all cathode types, essential for electrochemical performance. Manganese, M, stabilizes the cathode structure. Electrolyte and separator. The electrolyte contains volatile organic solvents and lithium salts, which pose fire and toxicity risks. Separators, though often overlooked, are critical for battery safety and are typically made from multilayer films of PE, PP. Proper handling of electrolytes is vital in recycling plants, as they can release hazardous gases upon exposure to air or moisture. Emerging dry processing technologies aim to eliminate liquid phase reactions, simplifying recycling logistics and improving safety. The proportion of these metals varies depending on the specific formulation. For instance, LFP, lithium iron phosphate, contains no cobalt or nickel, while LCO, lithium cobalt oxide, contains more than 20% cobalt by weight. The presence of these elements determines both the toxicity and recovery potential of spent batteries. Additionally, shifting market preferences toward cobalt-free chemistries is driving innovation in alternative recovery techniques. Anode materials. The anode is mainly composed of graphite, natural or synthetic, which acts as a host structure for lithium ions. Copper foil, used as a current collector and accounting for a significant portion of the total copper content in the battery. While graphite is abundant, synthetic variants are energy intensive to produce, raising questions about the sustainability of primary production. Innovations in anode recycling, including thermal and chemical separation methods, offer pathways to close the loop. The rapid expansion of the LIB market brings with it a parallel increase in waste streams, both from end-of-life batteries and manufacturing scrap. Industry data indicate that for every gigawatt-hour (GWh) of battery cell production, approximately 800 to 1,000 tons of waste are generated, particularly during the formation and testing stages of cell manufacturing. With the European Union aiming to scale its domestic production capacity to 1,000 GWh per year by 2030, the resulting production waste could exceed 1 million tons annually. In parallel, Eurostat data show that 99,000 tons of used batteries were collected across Europe in 2020. While this includes all battery chemistries, lithium-ion batteries represent a growing share. Forecasts suggest that post-consumer LIB waste could surpass 600,000 tons per year in Europe by the end of this decade. Combining this with manufacturing waste, the continent could face a cumulative LIB waste stream of 1.6 million tons annually, underlining the urgent need for scalable recycling infrastructure and logistics. This waste, if not managed properly, poses risks such as fire hazards from thermal runaway, environmental contamination from toxic electrolytes, loss of critical raw materials into the general waste stream. Conversely, if captured efficiently, it represents a massive opportunity for the circular economy and for reducing reliance on imports from geopolitically sensitive regions. The reuse of secondary raw materials could reduce greenhouse gas emissions by up to 90% compared to primary mining operations. In this context, national and transnational strategies must prioritize collection targets, safe storage systems, transport standardization under ADR conventions, and technology scaling for hydrometallurgical and direct recycling processes. The European Commission has identified raw materials like cobalt, lithium, and nickel as strategic and critical to the continent's industrial sovereignty and green transition. Recycling of lives is not merely an environmental duty, it is an essential element of industrial strategy. Europe currently imports over 80% of its cobalt and lithium, much of it from regions where environmental, labor, and governance standards are weak. Establishing a secondary raw material market based on recycling can mitigate these vulnerabilities. Moreover, LIB recycling aligns with several EU policy initiatives: European Green Deal and the goal of climate neutrality by 2050, Battery Regulation 2023 requiring minimum recycled content, Corporate Sustainability Reporting Directive (CSRD) mandating ESG disclosures, Raw Materials Act promoting secure and sustainable access. From a financial perspective, the recovery value of LIB waste is substantial. Industry estimates suggest that black mass derived from LIBs may contain metals worth between $1,000 and $8,000 per ton, depending on composition and market prices. Recovering these metals is far less resource-intensive than mining virgin ore and offers a quicker route to circularity. Furthermore, fostering a domestic recycling industry will generate skilled jobs, support regional development, and reinforce Europe's leadership in green technologies. Establishing urban mining hubs close to major EV assembly plants and gigafactories could minimize transport emissions and optimize reverse logistics networks. The development of standards for second life applications of LEBs, e.g., in stationary energy storage, further enhances the economic viability of circular strategies. Batteries that retain 70–80% of their original capacity after vehicle use may still provide value in other sectors, delaying final recycling and maximizing life cycle efficiency. Thank you very much for watching this video, and see you in next module.